So in the last lecture, we were looking at this length expander bar. There's another diagram earlier than this, but I think this one will do. Yeah. And we went through, we didn't go through all the math, but it's pretty straightforward. We laid the groundwork for that. Yeah, and you can, the book may have a little bit more on that, but ultimately you got to sit down if you're interested and go through and derive everything. But we did it for no load. Remember, we set the stress at the faces here equal to 0. There can be no net force on a face because the face has no mass. So if you've got nothing on the outside here and no load, on this side, you would have in general a load. On the other side, you have the material. It can exert no stress. But there is a strain, which is different from standard classical theory of elasticity, and that's due to the piezoelectric nature here. So what we want to do now is generalize to a force. And you might say, well, why didn't you just do that in the beginning? Well, it's easier to split it up. We'll be able, the derivation you'll see is similar to before. There are parts of it that are very similar, essentially the same. So it's always good, and this is how a lot of people approach things, theoretically. It's the first thing you learn when you do theoretical research, is you start from something simple that you can solve, and then you build on it. You never go for the whole thing. It's crazy. Okay, so that's what we're going to look at now. We will show that this is the equivalent circuit. And again, it's useful. We're seeing it here. You're going to find it for problem sets and quizzes and stuff. It's useful. Brian's pretty good about this. Here are all these circuit elements here. Their values in terms of the parameters of the transducer are here. Incidentally, this is called a T network. We'll talk more about that at the end of the calculation here. So the first thing you want to see about this T network is that we don't have a two-port system anymore, right? We started off way back in chapter 2 with the canonical transduction theory with these canonical equations. We had two ports. Now, because we have two mechanical, there's two mechanical inputs or outputs here, we're going to have three ports. So here they are. There's two mechanical and one electrical. The generalization from 2 to 3 ports is not difficult. It's just what you would imagine. It's not a problem. Formally, from a basic theoretical point of view. We're actually not going to do that here, as you'll see in the end. There's no need. Once we've established this equivalent circuit, we don't care about all that, right? We work with this, Kirchhoff's laws in this. Okay. So, how do we begin here? We begin with there's this longitudinal strain. That's the primary strain, the one we're interested in here, in the x direction, and we deal with that. And remember now, we generalized this before to include the possibility of standing waves in here. So we're not necessarily at a sufficiently low frequency that it's uniformly expanding and contracting. We can have standing waves in there. We're being more general. The uniform expansion and contraction is a special case. It's the low frequency limit of our theory here. Okay, so we write down the general standing wave solution. Okay, so this is the displacement of a particle here as a function of x. And as I said yesterday, this is absolutely general. We have both, we're including all possible phases here. We can't just do this or that. And it's steady state. We're assuming there's a little bit of losses here, so the system's in its steady state. All right, we're not worried about transients here. The particle velocity here is the rate of change of the displacement with respect to time. That just brings down an I omega using our complex. These are in general complex. Everything's complex here. And now we evaluate this. Okay. We need, as before, we need to get rid of this. So here what we do is, the velocities, those are canonical variables. We're gonna stick with the velocities. Those are like currents, right? So we stick with those. We've got to put our boundary conditions in terms of the velocities, and that's quite easy. We just look at this at the two boundaries and set it equal to u1 for the left boundary and u2 for the right boundary. All right? And as before, similar to before, it's easy to solve for A and B. We get these expressions. And then, now it's very much like before. It's a little bit different here because we had a different, boundary conditions. But now it's very much like before. It's the same idea. We determine the strain, okay, which is just, and so we're going to skip these steps. I'm just going to go to the result here. But let me just sketch out what we discussed yesterday. We determine the strain as the x derivative of this, where we've gotten rid of A and B, right? Then we know E3. We know S1 then. There it is. We know S1 when we determine that. We know E3. E3 is very simple here, right? Yeah, E3 is simple, okay? We shove those into maybe I should go back and we shove these into the first piezoelectric strain relationship. Okay. We find the stress. We then put the stress in here, just what we did yesterday. Put the stress in here, and now we can find D3, and that's important because that's going to give us the current, which is an important variable. That's the idea. So same idea as the previous lecture, and let me just I'm just going to go to the result here. Like I said, the textbook may have a little bit more. In fact, yeah, I don't know if it does. I can't remember. I didn't check. But anyway, we end up with an important variable here, and that's the current. Of course, the free current, right? What we control. Okay, so now, as usual, due to the ease of electrical measurements, we consider the input. We're going to consider the admittance here because this is a lot simpler than the voltage is very simple. We have a uniform field, so it's just the field times the thickness. Incidentally, this is where I guess it first pops up here. I made a note here. There are two T's here. I never noticed that before. This is a thickness T, this is time, right? I think you can handle it. Let's not worry about that. Let's not redefine. It's not worth the trouble, right? And I'd never noticed it before. I just, you just don't see it. You know what this is, okay? But in a thesis or a journal article, you'd probably want to get around this somehow, in some way. There are different ways of getting around it, okay? But here, I don't think we need to worry about it. Okay, when we do that, when we find the admittance, we get I omega times something. That something will be the blocked capacitance. Blocked meaning this is not here. And that's the meaning of the blocked capacitance. It's what you see when you block the mechanical side. That's why it's called the block capacitance. So this will be listed in that previous page underneath the equivalent circuit. Now I'm not going to substitute the voltage here. We're not going to explicitly substitute it here because we're aiming at proving that equivalent circuit. And V is one of the quantities, natural quantities, the voltage in the equivalent circuit. So we'll just leave that. It's convenient just to leave that. Okay, now we've done the part of the problem. We've done what you see on the electrical side, we now have to connect the forces and the velocities, deal with the mechanicals, those two mechanical sides now. So there's going to be some stress, which I didn't write down, but which we know. Remember this? We found this. To get this, we had to find this. And this is in the, I think this is, I'm pretty sure this is in the book, okay? Explicit expression. So again, we look at a face, either of the faces. There's some force due to the stress. Then there's the load. Those they have to balance because the face is massless. So the boundary conditions are this. There's a minus sign because if you look back at the diagram, Brian has defined positive force as in towards the piezoelectric, not out. So that's why we got this relative sign here. We've seen this kind of thing before. It's usually not a big deal, but it's just something you just want to be careful with it because it can potentially lead to problems. So here are the boundary conditions that we have to have for our loaded linked expander bar. We now substitute T1, yeah, it's in the textbook. And here's what we get. Now if you look at these equations, these are looking kind of canonical-like. You know, we've got, not exactly, but you know, they have that appearance, right? We got the forces over here in terms of the velocities or the currents, and then we got voltages. Okay, now this has been simplified a little bit. There's a common quantity, impedance, Z naught here. It's just about everywhere. And it's defined underneath the equivalent circuit in the textbook there. Okay, and then there's an N. It's natural to call this N for reasons that, you know, for transformer reasons. Define this, okay? If this bothers you, you just treat it as an abbreviation for whatever quantity sits here. And again, you can look it up just below the equivalent circuit. Okay, now it's sort of interpreted. To make the final step here of comparing, just showing that the equivalent circuit is indeed the equivalent circuit, we need to first of all do some checks, some symmetry checks here. We have a symmetrical situation in the sense, I mean, this could be physically, you could be exerting any kind of forces here. It doesn't have to be a symmetric response of the system. But theoretically, I know that if I interchange all one subscripts with two subscripts, if I interchange one and two subscripts, I've got to get the same equations. These equations have to be symmetric. Because we have this, it doesn't matter if we call this 1 or 2. I've got to get the same equations. They have to possess that symmetry. So the first thing we do here is we check that. And you'll notice that if everywhere you see a 1, you put a 2. And everywhere you see a 2, you put a 1. Before you change it, you have to, right. So here's our equations. This becomes U1, this becomes U2, U2, F2. You'll see that this equation becomes what? That equation. And similarly, you start with here, interchange 1 and 2, you're going to get that equation. So it has that mathematical symmetry. Now, to head towards the circuit, we're going to Brian introduces two other impedances called Z1 and Z2. They're defined. Okay? In fact, you can see what they are. This is going to be Z1, okay, in terms of Z0. Here's Z1 again. And there's going to be a Z2. So now we've beaten it down to a very simple looking form. And at this point, it's very straightforward to show that the circuit is, in fact, an equivalent circuit. Oh, I'm sorry. I did the symmetry. I did the mathematical symmetry up here. In the notes, it's here. It's easier here. Interchange 1 and 2. You get the same set of equations. All right. Okay. Now, just so you'll recognize something here, why it's called a T-network and why it's symmetrical. This doesn't look symmetrical, right? You got this hanging off to the left. But you can easily imagine pivoting the electrical side here with the transformer. pivoting out so that it's coming straight out, right? And then you can see the T, and you can see the symmetry. And that you can see the symmetry. Okay. So if you look at the equivalent, this is the circuit. It's got the classic block. You know, the first thing you see there electrically is a capacitor, and if you block the system, if there are no currents or velocities, that's what you see. That's what you see is C naught, and that's just what we have here, as we already said. If you look back, it's just what we have here. When it's blocked, we see this C0, which we identify as the blocked capacitance. So the circuit is right. It's right in that regard. Okay. You'll note here that there's going through Z2, there's a current U1 plus U2. And you can see that's exactly by Kirchhoff's junction rule. That's exactly what's going to happen there. Meets that, excuse me, it meets that requirement. That, you know, that has to be true. And now that pretty well nails it down. There's one last thing, the voltage. It's easy to do. Let's see. I'm going to edit. I didn't like this way this was said. Yeah. So the final thing here is using Kirchhoff's loop rule. For the mechanical sides, you can see that our theoretical expressions, our analytical expressions are equivalent to the circuit. So that's the equivalent circuit. Now I want to point out something here. We haven't put everything in nice canonical form. First of all, you have to have three equations. Where's the third one? You know, we would have to have a V. We have our V here. So this is not the standard canonical form. But who cares, right? We've got an equivalent circuit, like I said before. Once you've got that, further analysis proceeds by dealing with Kirchhoff's laws and the equivalent circuit. We don't care anymore. I don't think there's almost certainly no point in doing that. So this is not the strict canonical. We would need another equation. We need to have an equation for V. We need to get rid of it there. You know, you could do it, but what's the point? I don't think there is any point. Okay, any questions about that? So we'll be doing, I seem to recall, we'll be doing a number of problems with the length expander bar in the problem set next week, and there'll certainly be something on the quiz on this. And that'll help you see what's, get used to this. Okay, the next one, it's natural to think, this is called a thickness vibrator. So it's poled, again, always in the Z direction and electroded there in the Z direction. And now the length expander bar is transverse. You exert an electric field this way and it elastically responds this way. This is all in the same direction, right? And you think, well, okay, that shouldn't be a big deal. And it's thin, it's the opposite of the opposite. We're going to find that this is fundamentally different. There's several aspects of this. There's some similarities, but as you'll see, it's treated in a different manner. And it's just different. It's just different. It's actually surprising. I think I remember the first time I looked at this, I said, why are we doing this? Then I realized, okay. And an indication of why it's different can be seen right here. Now this looks pretty similar, but there's one big glaring difference. What is it? Yeah, this one, the negative capacitor. We've actually encountered this before in one of the 5 equivalent circuits in Chapter 2. But it's there because it has to be there, okay, to get the equivalent circuit. Okay, so let's proceed here. Excuse me. Now we're going to look at the case. This is I think this is the first time we've done this. Is different, okay? Usually what we've done is it's either low frequency or low frequency is a limiting case. We're not going to do that now. We're going to look at the higher frequency behavior. We're going to assume that the frequency is sufficiently high. There can be standing waves in here. It's sufficiently high that these transverse dimensions are effectively infinite. So we got this plate here. It's vibrating longitudinally like this, and it's essentially infinite in this direction. So the wavelength has to be small compared to these dimensions. What kind of, what's going on here? Is it bulging? No, this is unilateral compression and expansion. So that's different. And that's going to force us to solve this problem in a different way. As you'll, well, this is the standard approach. It doesn't actually require us to do that. But transducer people have found that you want to take a different approach here. Otherwise, it gets mathematically very messy. And I'll describe all that in a moment. But for right now, recognize that we're looking at, we can have standing waves here. The wavelength is small compared to L and W. So we're going to have a strain in the z direction. Do we have any strain in the xy direction? No. That's what unilateral means. The motion is just this way. So you want to realize something here. There's no strain in the transverse direction. So why is that important? Well, I'm looking ahead just a little bit, but it would be nice to use strain as an independent variable, not as a dependent variable, which we've been doing all along. This is what we've been dealing with all along. You'll recognize that. We think of it just in our heads. You know, the system doesn't care. You can trust me on that, I think. But in our heads, we see this. We think of T and E as independent variables and S and D as dependent variables. And that's all just in our heads. And that's what we've been using before. We've avoided this problem. But now we're starting to see, oh, it would be nice if we had S over here, you know, rather than T. Because we certainly have stress, transverse stress, right? Okay. Not only would it be nice to deal with S, but look at the electrical side here. Electrically, we've got this is, you know, there's this standing wave here. There's going to be some free charge. The free charge will be uniformly distributed. It's not like with a link expander bar. Remember, the linked expander bar, the free charge adjusted to keep the electric field constant. This is different. So now, the electric field is going to be complicated here. And we'll see this, but I might as well talk about it right now. When you have a standing wave in this direction, you know, you have this the polarization in there, right? When you have compressions and expansions of the polarization, what's going to happen? You're going to get a variation in the bound charge density. So the electric field is not uniform here. D is uniform because we have equal and opposite uniformly charged plates. D will be uniform. The electric field will not, and we'll see that explicitly in a few minutes. So, so here's what we're hit with. We need the opposite, in some sense the opposite of our standard approach here. We would rather treat D and S as independent variables and T and E as dependent variables. Now, we don't have to do that. We could proceed with these equations. It just becomes mathematically very messy. In fact, it's so messy that people take a different approach here, as I mentioned before. And here's the approach that they take. They say, look, there's nothing special about this. We can write down a similar set of canonical type equations, you know, stress-strain relationships, where T and E are the dependent variables, and S and D are independent, and T and E are dependent. Okay? There are going to be coefficients here. It's all linear. There's going to be coefficients here that depend upon the constants of the material. And you can solve for these in terms of these other constants. There's no new physics here. I want to make sure everyone understands that. There's no new physics. But for convenience, we're going to call this, you can see that because we flipped this, instead of dealing with a compliance matrix, it's now we deal with a stiffness matrix. It's like spring constant. And because it's for, because this is independent variable D here, it's going to be for constant or 0 D, those values. So there's nothing new here you could, if you wanted to, and I'm sure it's somewhere in the literature out there, you can find it somewhere, maybe on the internet, probably on the internet, but I don't know. You can find CD as a function of these other quantities over here. But we're just going to stick with this. In fact, this is so popular that you can actually look up, for different materials, you can look up values of these. People have tabulated values of these. So you don't have to, you know, compute them in terms of these other values. Now, while we're at it, and I've mentioned this, I don't know if you remember, we've mentioned it before. This is not the only possibility. There are a total of 4 possibilities for choices of independent variables, and you can see, okay? We've sort of gone to the flip side of this. Here's one, we've changed both of them, but you could just change one, okay? So here are all 4 possibilities. So they're going to have their own designated coefficients. The coefficients are all interrelated. There's no new physics. And Brian has a lot of this information in the book. You can look at it if you're interested. It's in chapter 3. We kind of skipped over it. I mentioned it briefly because I thought this was complicated, and you know, back then this was complicated. You know, so I thought it'd be best just to stick with that for as long as we could. Okay, so everything's what we're interested in is the 3-direction here. We specialize the piezoelectrics to the 3-direction, and now we get a simple set of equations because of our these are simple because of our choice of independent variable. Let me write that down. Okay, now just so you'll know here, what is this quantity right here? For no displacement field, this is the classical stress-strain relationship. And this is the modulus of unilateral extension and compression. This right here, okay? Because we talked about that long ago, right? This is the stress is proportional to the strain. And the proportionality here is the stiffness, the Hooke's law thing. And for what we're doing, because it's unilateral, this is going to be that modulus. So the wave speed is going to be what? The longitudinal wave speed. It's going to be the wave speed not for Young's modulus, but for the unilateral. So that's denoted, Brian denotes this. This gets a little confusing here. Okay, so this is not a stiffness. This is a compliance, okay? So at this point on, we're going to have, you know, we're going to have 2 indices on the stiffnesses. We're not going to think of it as a matrix from now on. This is now explicit, okay? We just care about that entry there. So this is, you can see, omega is equal to ck. This is a wave speed, all right? And it involves, it's the square root of the appropriate modulus, which is the modulus of unilateral extension and compression, divided by the density. Okay. So I guess we're calling this zeta now, so this is the displacement in the z direction, the only place there is displacement. And again, here we go, similar to before, right? General standing wave. And don't forget, you know, you want to keep in mind, this theory, all theories are restricted. In our case, the restriction, or one of the restrictions is, you can't look at this quasi-statically. You know, this will change. This will no longer. This will be different. Okay. Now, I have in the notes. I have something here. The notation. There's a little bit of a problem with the notation here. If you go back to chapter 2, towards the end, on the wave part, the elastic wave part, I think it's in chapter 2. I don't even know. Remember we talked about elastic waves, the general theory, wherever that was. It's not important. It's somewhere previously. Okay? This actually stood for transverse, for shear waves, I think. Okay? So there really should be an L here if we want to be consistent with that notation. But you know, as long as you understand the physics, there's no problem. We're talking about compressional waves here. The unilateral modulus is here. And he might have done this because if you put an L there, you might get confused with the transverse length dimension on the thickness vibrator. I don't know. Notation, I don't know if you've noticed, but notation is a big problem in this course. It's full of notation. I mean, it's just tons of bookkeeping, right? So we're not going to change. We're certainly not going to change the notation here. So we understand that that's what that speed is. Okay, wave speed. So the displacement field is simple. Okay, it's going to be uniform. The strain is how the displacement changes with z. That's our definition, actually, of strain. So now it's similar. This is similar to what we did before the linked expander bar. All right? We substitute the strain and the displacement field into the first of into the first relationship. I just have to go back one page, I think. Okay. So we've got an expression for the strain. This is really simple, just uniform. That allows us to find the stress. Okay, I can see, yeah, this is a little different, okay. So let me follow here. That yields distress. Okay, well, let me check something here. And I have here that this is in the tech. We're going to skip some steps, okay, like we did before. I don't think there's any need to plow through all the mathematics here. Brian has an expression I have written here, unless I made a mistake. I think he has an expression for T3. I didn't write it down here, okay? But you can see how we can get it. It's from the first piezoelectric strain relationship. So we've got T3. Now we've got boundary conditions. What are the boundary conditions here? Well, we're going to do as before. We're not going to be, sometimes it's not good to be too ambitious, overly ambitious. That's actually by definition. Overly ambitious means you're too so it's not good to be overly ambitious by definition. And we're going to just settle for the free case right now, okay? So the boundary conditions are, of course, no stress. So T3 has to be equal to 0 at z equals 0 and z equals t. Okay? Hold on, I just realized something here. I didn't make a note. Okay. So we have to have this, no question about it. This is unloaded. So similarly as before in several cases now, that's going to force what those standing wave amplitudes, A and B, have to be when you do that. So I'm just giving you the result here, okay? But if you want to pursue this further, you ought to look at Brian's expression and you can check it. And this is simple. So we have this for A and B. Now we substitute those back into the strain. And we now have this, and this is where I picked up on the two. I didn't see it, or I picked up on the two T's here, but it actually happened earlier. But we're not going to worry about that, right? Okay. So now we have the strain. What do we do? What do we do next? Well, you know it's coming. We dealt with this. Now we go here. Second equation. We substitute it into here. We can find the electric field. From the electric field, we can find electrical, we eventually get the current. And so that's similar to what we did before. So let's see what I said here. Right, so here's the electric field. And now, I don't think I had noticed this before, but you can, you see it's complicated. It's non-uniform. It's a standing wave. It's got standing wave character in there. And I think that's because, due to the standing wave in there, we have this polarization, and there's going to be, see, the electric field is sensitive to all the charge, not just the free charge, but the bound charge too. So due to the standing wave in there, we're going to get these clumps of alternating charge, and that influences the electric field. So the voltage, to get the voltage now, we actually have to integrate. It's not constant. You can't just multiply it by the thickness. And even if you thought you could, you'd immediately hit a problem. What's Z? What do you choose for Z here? Well, the answer is you don't choose it. You have to actually integrate, okay? So the result of that, we'll just set it down, stated here. Here's the result. So now, this is a little bit different than before. Before we dealt with the current, and it was complicated, and the voltage was simple. But now the voltage is complicated, and the current is simple. The current, as we've seen several times before, is I omega times the free charge. The free charge is dictates the displacement field. So you use Gauss's law for dielectrics or macroscopic media to get this. So now, are we going to deal with the admittance? No. We're going to deal with the impedance, right? We don't want to deal with 1 over a complicated quantity like that. So now, here is the input electrical. It's capital letters. Remember that? I haven't reminded you that for a while, right? But it's capital letters. So it's electrical. There it is. And now, I've been sort of neglecting to tell you this, but you know, this is not a very complicated form, and the reason is because, you know, they discovered that half-angle identity for the tangent that is unusual, that we talked about previously. So we've used that identity here. Also, there's a bunch of constants that have been lumped into this k squared here. This is a coupling factor, an electromechanical coupling factor here, in the thickness direction. Okay, so what that is, I didn't even bother to write it out, and the reason is it's going to be with the equivalent circuit. Now we haven't shown this equivalent circuit yet, but it is, oops, wrong way. But it is, but you'll see here, it's right here. You can see why, incidentally, from just a notational point of view, you can see why there's a T here. We got to make sure we don't get confused with the K, right? So this is a square coupling coefficient here. In terms of the parameters of our system, and it's now parameterized with our new independent variables, right? S and D, right, S and D, because those are the simple variables here. So that's why you're starting to see these new things, this H here. Okay, and this D superscript is new, okay? That's referencing the fact that we've switched independent variables. Okay, so here's the impedance. So how do we interpret this? Well, and this is not immediately obvious. This is mechanical. There's mechanical stuff going on here. You know that that's true because there's a coupling coefficient here. It's coupling the mechanical to the electrical. So that's one reason. I don't know if that's such a great reason, but you'll notice it's got the standing wave character is in there, okay, which is a mechanical thing. So when I guess it's not clear at this, I don't know if it's clear at this point, but when we block the system, when we block those upper and lower plates there, this is what you're going to see. You're going to see a capacitance, and it's C naught, the blocked capacitance, which is also, of course, listed just below the circuit. Okay, so what we're going to do now is we're going to stop here. Oh, it's early. That's interesting. I think it's good to stop here at this point. We'll discuss the equivalence. On next lecture, we'll finish this and discuss the equivalence of this circuit with the actual thickness, the thickness vibrator. Anybody have any questions or anything? So the lab reports are due Friday, right? And it's going. I think it's going okay. I'm meeting several groups this afternoon. Okay. And there's an experiment this afternoon. All right, and Monday's a holiday. President's Day, I think, I don't know.
Yeah.
Is that right? Okay. Okay, any questions or general comments about anything?